Okay, sorry about that. Just about ready now. I wanted to load up the new set of slides for you, so you should be able to see that. Going to basically be trying to get through both of these sets today. I think we can. But before we get there, I wanted to ask if anybody had particular issues with the homework. We will go through them during the exam review, because your next homework I'll post today will be shorter. It'll just be kind of the granular filtration, which we'll cover today, and then membrane filtration the next couple lectures. So I plan to go through all of them at the same time, but if there was something particularly pressing or you felt like you really needed help with a particular problem, I'm happy to discuss it today. So if you've got something specific, yeah.
For number one, part B, I just kind of had trouble trying to derive the equation with both the zeroth order and first order in the same thing.
Yeah.
Because like I got an end equation, I was like, it looks like it would make sense.
Right.
But when I tried to like go back and like derive it, like Heidi showed us in class, I was like, there's like 3 equal signs of equation. I'm not sure.
Okay. So when we're deriving a first order decay equation at steady state with a zero order growth, right? Okay. It's a good question. And I created that problem and gave it to you guys. And then yesterday I was like thinking it through and I was like, this is kind of an interesting solution. So I'm going to skip forward 1 second and just use a little blank space. So in that problem, I guess that's 1B in the homework, you have a steady state system. So it's going to be, it was a batch reactor, I think. So, yes. Right? Yeah. So in a batch reactor, we had, so at steady state, so we have zero accumulation is going to be equal to that reaction that's happening in the volume that's a decay reaction. So this will be negative V. We have some sort of K, and we'll say C as the concentration. And then we have a growth reaction, which is going to be V, K, and then C to the 0 power, which is just 1. So that's how I would set it up. And then when you go to solve for C, it's feels a little awkward because then you say, okay, well, VKC equals VK, so C equals 1, right? It turns out, like if you stop and think about it, if you've got some set amount of growth over time and some proportion of decay, like whatever you have in there is decaying, the only place it can reach steady state is at 1, because that's a spot where the relative decay can decay relative to how much is in there, and the whatever growth factor, turns out that's just 1. So it's weird. I want to actually do some more thinking about it myself as to, like, maybe we could try some test cases and stuff, but kind of an odd one. But this would be the way I would approach it, right? Okay. So yeah, I'll try to elaborate on that a little bit when we go through the full homework solution, but that would be my initial thoughts there for you. All right, any other questions or concerns? Okay, so last time we left off talking about sequential reactors a little bit. These are not notes from last time exactly, I just left them up here from a previous time. We did talk about how we could sequence these and then have some number of reactors. If they're all the same, we can have just that same 1 over 1 plus theta k for a first order decay reaction to some x power, where x is the number of reactors. So we could have something like that. We could flip it on its head and say, well, what about n2 over n naught? Or we could do n naught over nx or whatever. So we can adjust it algebraically, but it's going to work out in the same manner because we can multiply. On the left here, this is not just a label, it's also a fraction, right? This literally is n1 over n naught or n2 over n1 or whatever. So because that's a fraction and we know its relationship to the reactor parameters, we can combine them in that way and then expand. So just like we showed here. Okay, with that, if you'd like some practice, I have a problem here. Given that we're going to try to go through all our granular filtration stuff, I'm just going to skim over it and leave these solutions up here. But this is essentially a sequence of two reactors where we have bacterial growth. Each have some sort of a rate constant. We have a flow going through them. And they are incoming. We have an incoming bacterial concentration. And then the question says, what is the final concentration of bacteria if the first one is a CSTR and the second one is a plug flow reactor? So another kind of example here of, well, what happens if we have two reactors, but in this case, they're not identical. In fact, we have one CSTR, one plug flow. And really, at the end of the day, we can do it because we can isolate the mass balances one at a time, right? We can do a mass balance here, and then a mass balance here, and then kind of use the inputs for one to inform, or the outputs for one to inform the inputs for the other. So that's kind of the big picture there. And if you just take a quick look at the derivations, I say, okay, for the CSTR, we start with our typical mass balance, steady state, and we have N1 equals N naught over 1 minus theta K. It's a growth reaction. And then the plug flow reactor, we have a similar thing, and we can come out with a final answer. We could also do the same problem and see what happens if it's reversed. I don't think I did that here. So if you'd like that, feel free to take that as a practice problem and make sure you can work out the same answer. Okay, so with that, I want to go to filtration. So we'll talk about both granular and membrane filtration. Essentially, we have two classes here of filtration in terms of physically what's happening to the stuff we're trying to remove with the filters. So we've got granular filtration, which is not actually size exclusion necessarily. Most of the time when we think about filtering something, we kind of think of like a screen mesh, a kind of a macro level, on your porch or something you might have, or in your windows when you start opening them because it's getting nice outside. You have a screen mesh there so that anything the size of a mosquito or larger can't fly through it, but the nice air outside can go through it, right? So that's the principle of a size exclusion, right? So membranes typically operate in size exclusion, where if we have some particle and it's trying to go through, we've got water going through and out, that particle then gets stuck and is excluded by size on the surface there, right? So that's the difference here, whereas a granular filtration system, we have water and it's going to be pushed through this bed of sand or granular media. So if I just pretend that's full of sand grains, this is our granular media. Then water is going to be pushed through it and out. So we'll say maybe we'll collect it that way. And as it's going through, if there are particles that are larger than the space between the sand, yeah, there's some size exclusion. But really what we're after is some of the smaller particles that maybe made it through our sedimentation Perhaps our clarifier is not actually perfect and there's still some particles suspended. Maybe there's a little bit of turbulence there at the end as the water's harvested. So some of the particles come out, and our sedimentation design, it's reality, not the ideal picture that we like to draw. So this then gives lots and lots of space for those particles to stick to the sides, the edges as they flow through, or to even sediment in the little spaces between the pores, or to find each other and coagulate further inside this porous media and then get stuck. So there's several methods that we can talk about, and size exclusion is only a small part of the picture for our granular filtration systems. A good example here, I talked about the screen porch for the size exclusion, but on the granular media, if you've ever used like a Brita filter, if you have a refrigerator that you need to replace the cartridge every now and then for the filter, really what that's doing is that's a carbon filter. So it's activated carbon. Activated carbon has a lot of surface area, and organic chemicals, like to stick to that much more than they like to hang out in water. So water is very polar. This activated carbon is not very polar, so it's very attractive to non-polar stuff. So you could take, let's say, some coffee where we have caffeine and other flavors and things, run that through a carbon filter, and a lot of the molecules that would rather be hanging out with a non-polar surface will just stick there and be removed. So you could potentially filter out all your coffee with a Brita filter and remove a lot of the coffee itself, right? Or tea. Probably not everything, or maybe you just need a lot of carbon and repeat cycles or something. But you could get it back to pretty clean water after steeping it in the coffee or the tea. Okay, so that's adsorption. So there's some of that going on with particles, but if we're just talking about particles, there's also these other sedimentation, impaction, other stuff. Size exclusion then would be your coffee filter that's trying to keep all the grains, out of your coffee. All right. At any rate, so let's get into some of the mechanisms here for granular filtration. Like I said, it's really about what's happening to these little particles as it's flowing through. So we have maybe a little mechanical screening. Like I said, it's a particle, and it just doesn't fit. Sure. But if that happened to everything, it would clog up real fast, and we'd have to clean the filter much quicker than designed, because just water won't flow through it because all the pores are clogged. So normally what's more often happening is maybe we're getting some sedimentation as this little particle here is traveling through. It can actually just fall faster than the water moves to the side here. And so then it ends up sticking right there as the water continues passing. So it's like a million little tiny sedimentation chambers, so offering more opportunities for sedimentation to occur. So that'd be one of them. Flocculation can occur because we've got, not very turbulent conditions here, but reasonable mixing with the water just sorting its way through the pores. So particles can then find each other. They're kind of confined to the small little areas between the pores anyway. So there's going to be a lot of cases where two particles find each other, and then they create this one larger particle, and then they get stuck, or sediment, or whatever. We could have what's called interception, showing these particles just going along through. The water just narrowly edges by that grain, and it just kind of gets stuck because it happens to contact the side there, and the particle gets stuck and continues on. Last one would be impaction. A little bit like what I was talking about with sedimentation, but simply the water is going too fast here around the bend, and the particle is right here, doesn't move at the same speed as the water exactly, right? So it's, in some sense, it's about the same as sedimentation, but it's just, if you take the turn too fast, the water makes the turn, the larger, heavier particle does not make the turn, and it impacts the salmon. sand grade or whatever. So all of these little mechanical or physical aspects, you can imagine these are also improved by kind of that chemical coagulation that we would have done before this stage. Sometimes you can, if you don't have too many particles, you could even skip sedimentation altogether and just make sure you have a robust granular filtration system. You do the coagulation, give it a little bit of flocculation time, and then send it through. And that destabilization will cause the particles to stick really well to your granular media and to each other inside. So that's kind of the why it works and kind of how it works on the micro scale. On the reactor side of things, now we can be thinking about, all right, well, how is this going to work in practice? And in my lab, we have this setup. So what I think I'll do is next time, I didn't think to warn you today, but next time, plus I think we're going to try to cover a little bit too much material today. Next Tuesday, I'll invite whoever's interested, the last 15 minutes of class, to walk over to the Engineering Annex Laboratory. It's just right across from PFT, to go and see this little unit and play with it. Essentially, we have 3 columns here. Each of these contain granular media. This particular unit is more often used for iron and arsenic removal, but it is the same principle in terms of a granular filtration media. So this is less designed for particles, although it would remove some, and more designed for stuff to stick on, like I was talking about, the Brita filter. It's a little more of that style where we want chemical adsorption. And you see in practice here, there's another column-based system where you have a little more pressurization because you're keeping the granular media a little more confined. In most cases, it's not actually this column-type system. Most of the time, we have what we'd call a bed, like a filter bed. So this is kind of the more standard. Both exist, both are used, but the standard bed style is really, that's kind of what I drew earlier. You have some media, and then you stack up the water on top of the media, which then the gravity by itself is exerting some force pushing it down through the water, through the granular media. So in either case, you're getting the same effect. With the column systems, you can usually have a little bit higher production rates, just simply because your sand is confined a little better, and that added pressure is not going to cause as much problems as it would in an open bed like this. Okay, so this would be an example of a system in reality. I'm not actually sure where this is, but it looks kind of fun. You see here I've outlined one of the beds, so it's very likely that they have these catwalks and stuff, but this is probably just one bed here, and so that's a long and wide bed where they're going to fill up water, and it's just going to be constantly pushing through until they need to clean it. Okay, so just a little bit of history here. I already touched on a little bit of this. The media is typically some sort of a sand, but very controlled in terms of you want consistent size, so it's gone through some sieving or other processes to make sure you have kind of a consistent grain size and density. Could be anthracite, which is it's a mineral that's acts a lot like activated carbon, or you could use directly granular activated carbon. The history for this type of filtration actually dates back to the 1800s, where there were slow sand filters. We called them slow because really they were, you put water over kind of a sand bed and let it seep through. And it was actually such a slow flow rate that really what you were getting is biological treatment. So there's kind of like wastewater treatment in a sense. And you'd get improved water for letting it go through. Of course, back then, we wouldn't really have very much in the way of even pumps or things to handle the water so well. So that, and maybe there were, I'm not sure actually, but not nearly as effectively as we would have now or commonly. So it would be a pretty rudimentary way to improve the water quality, but it would have some improvement. That's why today we call them a rapid sand filter, just kind of to juxtapose with those slow sand biological filters. Okay, a few terms then to use when we're describing our operation. So, and actually before we get there, most of our operation really is all about defining and designing a proper routine regimen to clean our filters. Because they're going to get caked up, they're going to get nasty, they're going to be filled with particles, and eventually, if we never cleaned it, you just ultimately start having particles escaping because they're slowly meandering through the system. So essentially, if we caught a particle early on in the filter and it just like gets stuck pretty early, maybe hours and hours later, it will have worked its way through these little grains. Every now and then the water kind of pushes it a little further. Maybe something shifts a little. Eventually that stuff will start coming out, right? So eventually we would have breakthrough of the particles, which would be very bad. And then if we have any disruption, then maybe it gets shaken a little bit and all sorts of particles start spilling out. So basically we have to just clean it routinely. Because it's such a simple physical process that's catching the particles, it turns out it's pretty simple. It's a pretty simple physical process to remove them, right? So the backwashing process is very nice in a sense that this whole thing is pretty simple and straightforward, and we can then continuously use this granular media so long as we have a good backwashing cycle. Okay, so then a few terms to describe all that so we know we're talking about it. The first would be filter ripening. The first few minutes of using a brand new or freshly cleaned filter, essentially what's going to happen is, if you've ever done this with a Brita filter, you turn it on, you start pouring water through it, you get black specks of carbon coming out. So if you have a brand new filter, you're going to want to rinse it just to get out the junk. Or if you have just cleaned your filter, there's maybe going to be a little bit of particulate matter that was left over from the washing still in there and loose. And so that's going to come out. And we don't want that. And lastly, it turns out that it's actually good for the filter to have a little bit of stuff stuck to it to begin with, and then it becomes much more sticky to everything else. And maybe the sand grains have to kind of settle in and compact just a bit and get into place. And so typically about 15 minutes of operation is good for that ripening stage, takes care of all those things. I guess if it was a brand new filter, maybe you'd need more, but this ripening then is something like 15 minutes of normal flow through it so that we can avoid those issues. Okay, then we have backwashing. Backwashing would be flushing water in reverse. Mentioned it already. Sometimes we use an air purge as well. I'll take us through a couple videos just to experience that virtually in a few minutes. And that's to clean and regenerate the filter. Then we have terms to describe how we know when it's time to backwash. So we have first head loss. This is hydraulic head, so pressure, meaning the head loss is basically if we have the same amount of pressure being applied, how much pressure is still there coming on the outside. So if you are applying, let's say, 10 psi to a filter of some sort, and the filter has some resistance, it's going to take up some of that pressure, and let's say it's got a pressure drop of 5 psi across that filter. Then, whereas at the top we had 10 psi is our pressure in the pipe, then in the pipe in the lower we'd have 5 remaining. Okay, that's how a pressurized system like this works. That pressure is essentially consumed by the force required to push the liquid through the media. So then if we have that would be a 5 psi head loss. Usually we're going to talk about this in terms of the height of the water. So if in a filter bed like this, we have some height where we started up here. So height in meters. And over time, so let's say we would probably start here. It only takes a little bit of water. And then over time, the filter gets clogged up. It requires more pressure to put on top of it. And so then the way we operate them actually is we give it a constant flow. And so the water will build up to higher and higher layers and will automatically be pushing harder through the filter. So it's actually a pretty convenient way to, we know we can produce the same constant amount over time, and it'll just keep increasing until it's reached some sort of a limit. Either the height of the bed, we're going to overflow our beds, which we would never let that happen, or more likely, our concern would be if we give it too much pressure, at some point, we start getting concerned that the sand grains will just split apart, or we will channelize them, forcing too much water or pushing too hard. The sand will give way and structurally, and then you'll just have a channel or a fissure, and all our contaminants will go through. So we want to avoid that. We can't do too high pressure. Columns can hold them a little better in that manner, which is why we can go a little faster with those. Okay, last thing is turbidity. We've already talked about this. Should be nothing new. It's a measure of the number of particles in solution, and we can measure that with light scattering. The NTUs is a typical nephelometric turbidity units. Typical way to measure them, and essentially we can monitor the turbidity because particles are really what we're removing with the filtration. So if ever we see high turbidity coming out, we realize, oh, we need to stop operation, right? So we want to be cleaning the water. So if we ever find turbid water coming out, that would be a problem. Just a quick little bit about how we measure turbidity, in case you're ever curious. This is how you do it in a lake or natural water. Have a little Shecky disc, and when you can no longer see the distinct lines, we can kind of say, okay, well that's the limit. And essentially, it's the light scattering of the water that's causing that change in the visibility there. Okay, so how do we know when to backwash? So we just talked about the turbidity. There's really three methods we use. One would be that head loss limit. So at some point, we have too much pressure that we have to apply. The water is stacked up on top of the filters. It's stacked too high now, and we're worried about it being causing issues for the media itself. We could just put a time limit on it. We know that about every 96 hours is the limit, and just based on the operator's experience, they're going to design it and say, well, it's never good to operate much past that 3-day mark. We're just going to filter, or we're just going to clean it after 72 hours or whatever. It could have also a turbidity limit, and usually that's going to be combined with the other two. So it's like either 72 hours, or if we hit this turbidity limit, we're just going to stop and backwash. So if we think about what's happening to the turbidity over time with operation. So let's say we have time in hours, and what I'll say is we will have a cleaning event here, and then we start, and we have I'm gonna not quite draw this to scale, but then I'm gonna say this is that rinse or ripening here, and then we have operation for, so I'll just say production. So this is when we're producing clean water. You have a production phase. Hopefully that should be pretty clean. In fact, that's going to mean I need to draw that there. Let's do this. So we'll have this production time. Ideally, that's clean water. And then at some point, we have a cutoff where we say, all right, well, now we need to backwash and clean again. Okay, so that's our total cycle lifetime, and then it repeats, right? So that's why cleaned, that's the same as backwash, right? So we can repeat those cycles like that. So if that's our system, and this would be the cycle end, what we can say is if we add some sort of turbidity limit, let's say like here, anything above this we say cannot be used safely. Then we track our turbidity. It's going to use a different color. While we're rinsing, it probably is going to look something like this. And then as the filters are now ripe and they're operating well and we're nice and clean, within just those few minutes, then we're on to kind of a typical, like a fairly flat turbidity with slowly increasing up until some point, and then we cross over the boundary. So in this case, if we had a time limit that was right here, that would work fine. Or if I were to draw it perfectly, I'll try to get another drawing here. We could say that this is going to cross right there at the boundary and say, aha, right there, that's a problem, right? We just crossed, and so now we have to stop and backwash, right? So that would be kind of how our turbidity limit would work. And that's probably a reasonable picture of how the turbidity would look like in a backwash, in a typical system, right? During our rinse, we are over the limit here during the rinse phase, some amount over the limit, and that's a problem, so we don't use that water. Sorry. But then quickly we are back under the limit because the filter is now ripened and ready to go. All right, does that make sense? Okay, so it'll be good to think about these the filtration cycles in terms of this. We start with a clean thing, we ripen, we produce, then we stop and backwash again, right? And sometimes we might have a little bit of time added to that backwash step for air purge. Okay, just to elaborate a little bit more, so we'll say this is the cycle start. Then we have that rinsing. Let's see, rinsing / ripening. And I'll say that's typically 15-20 minutes. Then we have production. That's usually on the scale of hours, anywhere from maybe 24 to, 96 hours. Just really depends on the system. And then we stop and have a backwash. And actually, I'm going to say, if we're going to be very thorough, I'm going to say air purge if we have it. That's part of the backwash. And then we do have to backwash with water for sure. And then that's the end of the cycle, and we would then start again, right? So this air purge, maybe that's 5 minutes, and always backwashing is about 15 minutes. I mean, I don't know if it's always about 15 minutes, but we always backwash with water, which would be about something like 15-20 minutes. So in total then, our operation consists of a lot of production time and a little bit of downtime. And one thing to note here is that downtime, we are using clean water to do our backwashing, right? We don't want to use dirty water to try to clean out all the dirt. I mean, in a sense, it might make a little sense, a little bit of rationality, but then we're also filling up our lines that should be clean water with dirty, contaminated water. So we don't want to do that. We want to use our produced water to backwash, and our clean water. Well, actually, at the start, we're not using the clean water, but the backwash we would be. So, all right, but we'll come back to that in a moment. For the head loss, we talked a moment ago about what it would look like in terms of the turbidity limit. Well, the head loss limit would probably look something like this. If we drew a limit, and that's our stopping thing. This was our cycle start. This was the ripening phase. And we have the production. and then we have our cutoff. Well, this one actually looks a little simpler because the head loss isn't really going to be changing very much. It's just going to be a slow, constant rise in pressure because the filters are clogging. So even in the ripening stage, it doesn't really do too much. And if that's just, kind of in minutes, it's not really doing much. And then over hours and hours and hours of operation, we then hit and say, okay, well, there's our limit. We'll just say it's like right here. There, then we stop and backwash. Okay. All makes sense? All right. So, just a quick showcase of what this looks like in practice before we do next part. Okay, so they're air purging now. This is the water that's sitting on top of a filter bed. It's probably a few feet of water. Looks pretty nasty. So this goes on for a couple minutes. I'm going to turn the volume down for a moment because the next step they're going to prime the pumps after having all that air in there, and it's quite noisy, so I'm going to try to avoid that. Give you a small experience of that, not the full deal. Okay, so they're stopping the air now, and then doing that very lovely air purge. Purging the pumps themselves. Priming. Still awful noises. More awful noises. Okay, so then they're just about done. Okay, so the pipes are then primed, and even if you look on here, that's 4 minutes in, so that whole air purge plus priming took probably about 5 minutes. I don't know if they started the video right when they started it all, but you can see it's actually matching with what we were saying. It's like about 5 minutes to purge this thing with air.
Fill the water for a bit. It's all warm. It's all bubbly. This is how they make root beer. Giant.
So this is how they make root beer. You'll see in a moment. It's an app's description. Okay, so they've given it some time now. It's constantly pushing water up and back through. It finally overflows to these troughs, and then you have that nice root beer colored. So that's all the junk that had been collecting for the past however many hours in the filters, preventing that from going into the your drinking water, right? Now, it probably is also containing some of the coagulant that was added, of course. So normally, the operation is reverse of this. You have water, your water that you want to treat coming into this main middle trough, and then overflowing and distributing across these smaller troughs into your bed. So normally the operation is literally reversed from this, where you have that water just flowing through into that trough and into those smaller troughs. So they just literally reverse the process and then change where this water is going. Instead of coming into that pipe, the water can go out there and go to a waste line to be processed by a wastewater treatment process. Sometimes, since they have the water treatment operators right there and they all kind of know water treatment, they'll have a small-scale wastewater treatment system on site, or sometimes they'll just have it hooked up and set up to send that to a larger facility for municipal treatment. So that's some backwash for you. So it's kind of neat. There's some other examples. The color of the particles will change from place to place, in part just either from the coagulant they use or the type of the type of soil or kind of organic matter that's naturally in a system. So there's some others, if you follow the links to other recommended drinking water treatment filtration units, like I do sometimes, you'll see like some orange stuff coming out, or some just different colors. Okay, so that's that first bit. I have another set of slides to go through. Any questions or comments on that? All right, so the next part I want to talk about is then how are we going to design a system given that we do have to stop and use our water to go back through and kind of filter stuff. Like, how do we design it then? We talked about this part already. We have these criteria. So how do we put it into practice? Well, really the end goal is how much net water are we producing over time? Because that's really the ultimate criteria of what we have to meet, is some amount of flow rate, right? We have to serve a community of X number of people, which means we have to provide X amount of cubic meters of water that's been treated per day or whatever. We have some flow demands. So how do we do that then if we have to stop and make use of some of the water we already produced, and we have to stop filtration sometimes? There's an important question there, and the answer or solution to that question is in part redundancy. So we're going to have multiple filters being used at once in order to ensure that we can take some offline during the process. So if we can take some offline and we have enough production outside of that, that's the ideal case. So we don't have any moments where we say, oh, sorry, you don't get water today because we had to stop and maintenance a filter, right? And it's even better if we have enough redundancy to say, oh, well, we were not expecting to have to maintenance that filter, but now we are. So we usually design it with some safety factor as well. Okay, so that's kind of the why, and now we're going to get to some math that helps us get there practically. So a typical production rate for a given filter, we can describe it as a production rate, which is a flux essentially, and we will come back to the flux concept with the membrane filtration. But a flux is essentially through some plane. So I'll say the plane of the surface of the filter bed. So two-dimensional plane. We have some water going through, and normally it would be a flow rate, and then we have some area. So essentially this flux is a flow rate divided by area. So if this is area, meaning like length times width. That's our flux, and so that's going to be in a velocity type of arrangement, right? If we take the flow rate, divide it by area, it's cubic meters per second divided by square meters of filter bed area, that gives us a velocity. Okay, so with that type of a terminology, and we see it written here as 5 to 25 cubic meters per square meter per second, we could see very easily that's 5 to 25 meters per second of water through the filter. That gives us a way, or a convenient number to use when we're scaling it, to say, oh, well, we have 20 of these filters in this ginormous treatment plant. Each of them are 100 square meters. So therefore, we're producing, 20 times 100 times I don't know, 5 cubic meters per square meter per second. So we could do that multiplication and scale it very easily based on how much filter area we have. We could also say, put this in terms of gallons and feet. This translates to about 2 to 10 gallons per minute per square foot. Okay, so in either case, it's the same type of deal. We would call this either a loading rate or a production rate for the sake of our granular filtration terminology, but it literally is a flux. So we'll come back to that flux concept a lot in the membrane side of things. So this loading rate then, or production rate, we're going to label this according to what our book says as lowercase v with a subscript a. And we're going to say that that's going to be equal to the volume of water put through the filtration bed divided by the area of the filtration bed times the time it took to send it through, right? So it's very much that volume over time, that's Q, right? And the area of the filtration. So we can literally write it as Q over AF. Okay, now one thing to note here is when we're talking about Q for this VA equation, this is not the Q for the plant total, right? We're just talking about the flow through one filter, unless we're talking about all of the filters combined. So I'm saying the Q for the plant is not equal to the Q to the filter. So when you're using this equation, you could use it if, like, for the entire plant, if you're including all of the filters in the entire plant, theoretically. But we don't really want to do that because usually we're going to have at least 1 or 2 offline. Just be careful with that and think about what makes sense to use. Maybe at the end of the day, you find some, if you wanted to know if all filters were running all at the same time, could you produce enough water? You could say, okay, well, all of the filtration area is here. We'll say AF total. And we'd have Q total. And then we see if our loading rate is satisfactory for that or something. Or maybe, as we'll see in a minute, we have some effective loading rate. Maybe then it makes sense. But just use some common sense here to see whether or not we can make a relationship with the entire plant. Normally, when we're talking about a loading rate, we're talking about a filter and the flow rate through that one filter. Okay, so just keep that distinction in mind so that you don't confuse that. So one of our goals, by the way, is going to be to find, instead of just VA, this is during production. One of our mathematical goals is to find, well, what's our net effective loading rate, including all the wasted time and water that happens when we do the backwashing and everything. So we're going to have a couple things there. Okay, so first of all, we want to take a look on efficiency of a filter on a water basis. So how efficient is this filter? This is going to be, we're going to use nu here, this symbol, as the filter efficiency. And this is only on a water basis, not on a time or flow rate basis. So here, we're simply going to say this is equal to the volume filtered, VF, minus the volume used for backwashing, minus the water used for rinsing, all that divided by the total volume filtered. So we're going to get that from VF, will be that during that production. Then we're going to use some water for the rinsing. And I'm sorry, I misspoke earlier. We are going to use that treated water. We're going to use clean water during that rinsing phase before we switch on. That'll just get the filters nice and as clean as we can get them before we begin. That's why we're having the minus VR here. We're going to use some clean water here for backwashing. So that'll be VB. And then here, this is just air purge. So we're not using any water, right? So effectively, that doesn't account for anything in terms of filter efficiency, aside from that's a little less time we could have produced water, I suppose. Okay, so each of these is going to be cubic meters. Will be our standard use. I guess you could convert them all to something else if you felt like it. Use gallons or something. Just need to be consistent. To find these volumes, it's going to be pretty straightforward, pretty intuitive. It's going to be that loading rate of water through the filter times the area of the filter times the time for that particular cycle or part of the cycle. I will note that sometimes we have a different backwashing rate than loading rate. So lowercase VA, this is our loading rate. We always use that for our rinsing. We always use that for our production. We don't necessarily use that for backwash. So the lowercase v, we'll say the backwashing rate. We typically use anywhere between 1 to 2 times the loading rate for backwashing, because sometimes the added speed kind of helps break particles off the sand grains and kind of disrupts everything. So sometimes in terms of time, if not in terms of kind of intensity of the mixing that's going on and the action we get, sometimes it makes sense to do that. So VB equals 1 to 2 times VA. So maybe we'll just use VA, the actual loading rate. If you end up encountering a problem and nothing at all is specified, it doesn't mention it at all, and you know that you have to make an assumption, it would be a fair assumption to say, okay, I'm going to assume it's VA. But double check that you don't have a separate way to solve for it, right? Because maybe the problem's actually wanting you to solve for that, given the time and the efficiencies you've been given or something like that. Okay, and each of these, as you'll see, the units will be square meters times that meters per second times time. So these units will always end up as cubic meters. Okay, and I do apologize for the awkwardness of having uppercase and lowercase v's. I've done my best to separate out them here for you, trying to make uppercase versus lowercase clear. This is how the book has it, so I'm going to keep consistent with that. All right, any questions or issues there? Pretty straightforward. So that gives us a filter efficiency on a water basis. Now, I mentioned a minute ago, how about that net loading rate or that effective loading rate? And here, thankfully, we're not using another V term. We're using REF, or it might actually be REFF. It just means effective, right? So the book uses this lowercase r effective as that effective or net loading rate. So this is a rate that's kind of imaginary in the sense that it's never operating at this particular speed, but this is the speed that it's operating at if you averaged all that time where it wasn't operating in all the water we used and wasted essentially during the non-operating times. So again, if we have production here, we make some sort of VF, we used some sort of VR, and we had some sort of V backwash that we used as well. Then we have time for air purge, time for, I'm just going to write that out, time for backwash, time for filtration, and the time for the rinse ripening stage. Then we can put all this together into an equation for this effective loading rate, which should ultimately be meters per second, so we can double check that. And that's going to be essentially VF, so the volume filtered divided by the area of the filter, minus the volume backwash divided by the area, minus the volume rinsed divided by the area, all that divided by the total cycle time. So what I'll say here is we can say this time for the cycle, or TC. And that can simplify very easily here and say that's going to be the volume filtered minus the volume used for the backwash minus the volume used for the rinse, all of that went to waste, divided by area of the filter times the total cycle time. Okay, so that gives us an equation then. This is not the efficiency, it's actually an effective loading rate. Now, if you're thinking about it, you might be tempted to say the filter efficiency times, which is going to be some fraction, right? It's not going to be 100% efficient. It's going to be something a little less than 100%. So actually, I'll just back up a step and say this filter efficiency is often something like 0.9 something. So 90% or better probably, which we would want, right? We don't want to waste too much of the water we're treating. So you might say to yourself, well, this times VA should be question mark about equal to REF. And the answer is normally yes. So it's a decent way to check yourself. But this is not necessarily true. And the big reason why it's not necessarily true is if we happen to need, like, let's say 2 hours for an air purge step where we're not using or producing any water, it's really going to set off our calculation here. So maybe we build in time where it's not operating. Maybe we just have to do some maintenance on something part of the system. That time is a factor in our effective loading rate. It's not a factor in our water efficiency. Okay, so the time there does become important in a sense of if we have time that's doing nothing, like the time for air. So this is actually not completely true. But usually close. So it's probably a decent way to check. And I'm just going to say T air causes differences, really. If we never had any time for air purge, it probably would actually be true because our equations are so similar. It's essentially, if we take a look at this VF minus VB minus VR divided by that area times the time, and we compare that with this one, it's that VF minus VB minus VR as it relates to VF. And so they're almost the same equation. Just one is giving a proportion on a water basis, and the other is giving us that speed. Okay, does that make some sense? All right, so then we really have two equations and some context to work with to solve some problems. And so let's go ahead and give this a look. We can finish this up next time if we need to. But here we have a conventional water treatment plant. We've got it treating 2.4 cubic meters per second of river water. Filters in the plant are 8 by 8 meters surface area and operate on the following schedule. A filter is cleaned once in each 24-hour period. The backwash rate is 10 liters per square meter per second. for a period of 8 minutes. It takes an additional 8 minutes to drain the filter and break up the media with air injection. That would be right before the backwash, really. Then of those total filter cycle time of 24 hours, 15 minutes is used for the rinsing of the filter after backwashing. During production, water is applied to the filter. So applied to the filter, that's setting us up to, like, that's our loading rate, at a rate of 5.5 liters per square meter per second. Okay, so it gave us a backwashing loading rate. It gave us a loading rate and a whole bunch of other information. So part A says, what is the filter efficiency? And then part B says, what is the minimum number of filters required by the plant? Okay, so go ahead and start working on that. I'll take a moment to just extract a little bit of information on the side. Feel free to use that or ignore it. But go ahead and give that a shot. So what we've got here is I've written some of the stuff out. I haven't pulled up the calculator for everything yet. But as we're going, I went ahead and wrote up the equations for you that we've covered today in class, and then recognize that we want the times for each of these units. So we're given the time for the backwash, given the time for the air purge, given the time for the rinse, and we were also given the total cycle time as 24 hours. With all of that, you might recognize that we actually don't have the time for the filtration, so the time we're using to produce water. And to get that, we just need to subtract all the other stuff away from the main cycle time. Right? So 24 hours minus the 8 minutes for backwash, minus the 8 minutes for air purge, and 15 minutes for the rinse. That gives us, if I did that right, which I did not, I just realized that I did 1400. 1440 minus 31 should be 14. Just treated that as if it was, so that'd be 1409 minutes. And that should give us, if we put that value in, we should be able to get a volume filtered directly. And one thing I'm noting here is I think I may have, earlier in the slides, I think I had it, I gave a typical flow rates that were much too high. I think I should have put them in liters per square meter per second, but I said meters, because these numbers are a lot lower than what I was saying earlier. So I'll correct those in the slides. Apologize for that. And if you were actually to think about it, 5 to 25 meters per second through a filtration bed, that's really, really quick, right? And so then if you were to do the math on that, that would just be kind of bonkers in terms of how fast water is moving through and how much water you produce. So I apologize about that, but I'll go back and correct that. That should have been liters, and what we notice here is because we need everything in meters, I went ahead and converted those, so 1,000 liters per cubic meter. So we had to divide each of these by 1,000 to get our values. Then it's kind of plug and chug, right? So we just need these numbers. We can get each of these volumes. We use these volumes directly into our filter equation, our filter efficiency equation, and we'll get that. And then given that, then part B is a little bit more interesting. We're going to need the effective loading rate and sort out something about the flow that's required for the entire plant, not just one particular filter. So do you guys have these volumes and the filter efficiency calculated? Two of the volumes. Okay, so which one are you missing? VB. Okay, so somebody calculate VB for us, given that. And what did you have for VF?
VF, I had 2.97 times 10 to the 7th liters.
Okay, so you did it in liters. So that should be times 10 to the 4th. That would be, I think, if I did that right, I think that should be fair. Sounds right to me. Does anybody else have a number like that? About 29,000 cubic meters. Anybody else get there? Okay, I can double check in a minute, but okay, what about VR?
VR, I got 3.168 times 10 to the 5th liters.
Okay. So if we take that to the 3rd, that'd be 316.8, or it should be take away the 3rd. So yeah, that also looks right to me, because if we're making 29,000 liters during the filtration, which is almost 24 hours, and then we just rinse for 15 minutes, it should be a lot smaller, but still a fairly substantial amount. So I believe them. I think that's similar to what I've done in past times. And the backwashing water was about half the time, but about twice as fast. So it should actually be pretty close to that 300 cubic meters.
Yeah, it is.
Okay, so what is that value?
3.072 times G.
Okay, and I just converted that to cubic meters. Okay, so then that gives us a filter efficiency. We do 29700 minus 307 minus 316. All that divided by 29700. Who's got that value for me? Gonna make me do it? No problem. Is it? $970. Okay. Okay, and that'll be unitless. It's a fraction. Okay, is that making sense? Kind of the steps there. Okay. So if there was a tricky part, that was probably in figuring out, okay, how do we get TF? Not to mention, okay, what do I do with this problem, because it's a new type of problem, right? Okay, so then for part B, we'll pick up there next time to take a look at that and how we would finish out the problem. Okay, so that's it for today. Have a good weekend. We'll see you on Tuesday next week.